So in the previous lecture we discussed about the effect of the neutral on the zero sequence currents, and then we extend it to find the zero sequence network of a different configuration of the transformer, that is star delta, star star, delta star, and the effect of the neutral on the zero sequence network. All these configurations can be summarized by the switching diagram of the transformer. This switching diagram takes care of all these conditions, whether the neutral is connected to ground, whether the primary or secondary is connected to star or delta, whether the neutral is not connected to the ground, whether neutral is connected to some impedance. All these are taken into consideration by this switching diagram. So the Z0 is the zero sequence impedance of the transformer. It is again taken to be equal to the leakage impedance, and S1, S2, S3 and S4 are the four switch which describes the condition of the transformer, whether it is in delta connected, whether it is in star connected, and whether the neutral of that star connection is connected to ground or not, and finally whether that star connection is connected to ground through impedance or it is connected directly to the ground. So S1 and S2 condition, S1 and S2 gives us the condition of the neutral of the star or the transformer on the primary and secondary side of transformer respectively. So the condition of the neutral of the star will be depicted by S1 and S2, and whether the transformer is connected in delta or not, that is depicted by the S3 and S4. So S1 is for primary of the transformer if it is connected in Y. S2 is the secondary of the transformer if it is connected in Y or star. S3 is again for the primary of the transformer and if it is connected in delta, and S4 is for the secondary of the transformer if it is connected in delta. So we can say S1 and S3 are for the primary of the transformer, and S2 and S3 are the secondary of the transformer. S2 is for the Y connection and S3 is for the we can say S1 and S2 are for the Y connection and S3 and S4 are for the star connection, delta connection. So if primary of the transformer is connected in star and it is connected to ground, then S1 will be closed. Otherwise it will always be open. That means even if it is in delta, if it is star, even if it is in any condition, but neutral is not connected to ground, in that case S1 is open circuited. So closed condition is only one, when the primary of this transformer is connected in star and neutral is connected to ground. Open condition if it is connected in star and neutral is not connected to ground, or if the primary is connected in delta, then this is open. Similarly for S2 case, if secondary is connected in star, if secondary is connected in star and neutral is connected to ground, then S2 will be closed. Or if secondary is connected in star and neutral is not connected in ground, and one condition when it will be open, another condition will be when the secondary is connected in delta, then S2 will be open. Or we can say in general, S2 will be open if the secondary side will be in delta, that is one condition. S1 will be open when the primary side will be in delta connection. Other condition for them to be open will when the neutral is not connected to the ground. S3 will be only closed when the primary will be connected in star, and S4 will only be closed when secondary is connected in delta. So otherwise they will always be open. There are not particular condition for them to be open, but there is only one particular condition for them to be closed, that is when secondary is connected in delta, S4 is closed, and primary is connected in delta, S3 is closed. There is one more condition for that to be taken into consideration, that is actually an exception. We will discuss that also. So S1 and S2 represent the condition of the neutral of the star of the transformer on primary and secondary side of the transformer respectively. That is S1 is for primary, S2 is for secondary. If the primary of the star primary of the transformer is star connected and its neutral is directly connected to the ground, S1 will be closed, that I have discussed. However, if the neutral point of the star is connected to the ground through Zn, S1 will again be closed with Zn in series with Z0. That means if there is some Zn like this, we may take this into account by placing it in series with Zn, but multiplied by 3. If neutral is not connected to ground, S1 will be open circuited. This is one condition. If the secondary of the transformer star is star connected and its neutral is directly connected to the ground, S2 will be closed. However, if the neutral point of the star is connected to the ground through Zn, S2 will be again closed with Zn to be connected in series with Z0. If the neutral is not connected to the ground, S2 will be open circuited. So this is for S2. For S3 and S4, if the primary of the transformer is connected as delta, then S3 will be closed provided 0 sequence currents are present in delta. This is very important. I will tell you when the time comes. For the time being, sometimes 0 sequence current are there, sometimes they may not be there. It will be closed when it is delta and their 0 sequence current should be there. If the secondary of the transformer is connected at delta, then S4 will be closed provided the 0 sequence current are present in delta. This also we have discussed. So S3 and S4 are mainly related to delta and S1 and S2 are related to star. So this is also to be taken into consideration before actually discussing a different configuration of the transformer. Let us start with this. Let us say we have primary is the star connected, which is connected directly to the ground. Secondary is also star connected, which is connected directly to the ground. In this case, you can see that we have primary star, secondary star, you can see, and both are connected to ground. S1 will be closed, S2 will be closed, S3 will be open circuit, S4 will be open circuit, and the final circuit will be this. So this is 1 dash 2 dash to be connected like this. So when primary is in star connected and neutral is connected to ground, secondary is star connected but neutral is not connected to the ground, you can say S1 will be closed, S2 will be open circuit because this neutral is not connected to ground. And since it is not delta, both these connections will be open circuited. Similarly for this, this is the reverse of this. It means S1 will be closed, S2 will be open circuited. Now for this case, we have star delta. This is actually usual case which we will face most of the times. This primary will be connected as star and its neutral is connected to ground, and secondary will be connected in delta. So the connection, that means S1 will be closed. Since primary is star, S3 will be open circuited. S2 will be open circuit since it's not connected as star, it is connected in delta. And since 0 sequence currents are present here, they will be also present in the this, and they will circulate in the delta. That's why we can show it as S4 will be, is it S4 or S3? Yes, S4. S4 will be closed, and the circuit will be like this. Similarly for this case, this is the same previous one, the other way around. That means delta is on primary side and star is on a secondary side. In this case, you can see that this S1 will be open circuited because it's delta, it's not star, and S2 will be closed because this neutral is connected to ground, and since S3 is closed circuit because this is delta. So for delta, S3 and S4 will be closed circuits, and for this and this one is same. Only thing is here we have put Zn. So we know that Zn will be reflected as 3 times Zn in the 0 sequence network and in series with Z0. It will be like this. S1 will be closed, S2 will be open circuit, and S4 will also be closed. This is for both the cases when both the impedances are present and both the windings of transformer are connected to star and connected to ground. This will be connected. S1 will be connected, S2 will be connected, and Z 3 times Zn will be placed in series with Z0, and 3 times Zn2 will be placed in series with Z0. S3 and S4 will be open circuit. Now this is the special case where you can see we have Y connected from the primary and S1 will be open circuit since there is no point of connection between neutral and ground. So since primary is star, this S3 will also be open circuited. Now what about this? Since there are no 0 sequence current on this side, there will be no 0 sequence current in the delta which may circulate in the delta itself. So we can show that this will also be open circuit S4. Here this and this circuit will this will be open circuit. This is also open circuit because it is in delta, it is not in star. So that's why what does this point mean? Provided 0 sequence current are present in delta. Since 0 sequence current are not present in delta, we cannot show S4 to be closed one. Similarly, for this case, this is an S, this is star on primary as well as on secondary side, but they are not connected to ground, so there will not be any 0 sequence currents. We can say that S1 is open circuit and S2 is open circuit. So this is actually the the different configurations of the star transformer, and we have discussed almost all the 0 sequence networks which can be made for different configurations. So let us summarize all the sequence networks of the different equipments. We have the type of equipment: positive sequence network, negative sequence network, 0 sequence network. For synchronous machine, we have a voltage source in series with the impedance, and this is IA1. VA1 will be equal to EA minus IA1 Z1. And negative sequence impedance, we don't have any voltage source, otherwise it are same. That's VA2 is equal to minus IA2 Z2. Similarly, 0 sequence networks, it will this similar network. VA0 is equal to minus IA0 Z0. It is solidly grounded. If there is Zn, then this comes out to be equal to minus IA0 into Z0 plus 3 times Zn. Similarly, for transmission line, it is the positive sequence network, negative sequence network, 0 sequence network. Of course, there will be 3 times Zn if Zn is present in the neutral. And this is for the transformer, and we have shown the switching circuit for determining the 0 sequence network of a transformer. So before going into some numerical part of this, we first discuss the practical values of 0 sequence impedance and their relation to each other. So for synchronous machine cylindrical rotor, we have Z1 is equal to Z2, definitely, because positive sequence, when we apply the positive sequence voltages to the synchronous machine and negative sequence voltage to the synchronous machine, they will have the same flux distribution in the space, but their direction will be opposite, because it is not a static device, it's a rotatory device. They will have the same value. Z1 is equal to Z2 for cylindrical rotor, and which will be very large as compared to Z0. I will discuss this why Z0 is very small. So Z1 is equal to the practical value is around 12% sub-transient reactance on their own rating, 20% is the transient reactance, and 110% for the synchronous reactance, that is steady state reactance. Z2 will also be equal to this sub-transient reactance, that is 12%, and Z0 is around 5%, which is actually close to very close to 0. In this case, this Z1 is equal to Z2 is ZD, that is the direct axis reactance or impedance, which is provided by the this synchronous machine, because it has actually two types of reactances, that is ZD and ZQ. Since cylindrical rotor, it is only ZD, there is not ZQ, because the air gap between the synchronous machine rotor and the synchronous machine stator is uniform. And Z0 is very small, that's 5%, it is very close to 0. There is a particular reason why is the relation like this. Let us discuss a bit about that, why we have small 0 sequence reactance and almost equal positive negative sequence reactance. This is the three-phase voltages VA, VB and VC, and this is the stator of the synchronous machine. This is the coil A dash, because it is wound like this. This is BB dash, because A, B and C, they are symmetrically placed in space 120 degree apart from each other, A, B and C, and their the negative part, or we can say other part of the winding, is shown opposite to that. That is A dash, B dash, C dash. When the current, let us say, is entering at this point, it will be coming out from this point. So in that case, when we use the right hand rule, you will see the magnetic flux will be in this direction. So this is the axis of magnetic field for phase A. Phase B will have this magnetic flux axis, and phase C will have this magnetic flux, because this magnetic flux will be perpendicular, or you can use the right hand thumb rule, you can get the magnetic flux direction. So first I will discuss what will be the flux pattern and total flux produced by the positive sequence voltages. You can see, let us say this is the positive sequence voltage, and at point P you can see VA has a maximum value, VA is Vmax, so VB is negative Vmax by 2, VC is of same value, negative Vmax by 2. When they are applied to this, they will produce the flux and they will produce the mmfs which are proportional to the voltages. So Vmax is in positive direction, that means it will form the positive direction Fa in the same direction and have the maximum value of Fa. So Vb, since this produces the Fb, but its value is only half in negative direction, Fb should have been in this, but it is in negative direction, so it can be shown like this. This is Fb, but Fb by 2, because in this case voltage is half. Similarly, Fc will be in this direction. So when we calculate its resultant, it will be 1.5 Fm. This is for when the voltage is at this point, omega t is equal to P. And this is the value of this rotating magnetic field, that is 1.5 Fm. Similarly, when we go to this point, point Q, you can see from this, these are actually the 30-degree points, 30, 60, 90, 120, this 150. That means from this to this we have a difference of 60 degrees. So this is for the first case. The second case, at omega t is equal to Q, at that time VA is equal to Vmax by 2, VB is again equal to Vmax by 2, VC is equal to minus Vmax. So that's what I have written over here. VA is equal to Vmax by 2, VB is equal to Vmax by 2, VC is equal to minus Vmax. So FA will be in the same direction because it is positive. FB will also be in the same direction because it's positive, but it will be half. FA in this direction, half. FB in this direction, half. But FC will be full but negative. So FC will be full. When we use its again its resultant, it comes out to be equal to 1.5 Fm, and you will see from this to this you will have a change of direction by 30 degrees, but the magnitude remains the same. This is actually the concept of a rotating magnetic field. And when we go for negative sequence, at this point we will have Vc, at this point we will have, let's say, Vb. In that case the direction will be, for this case it will be almost similar, but the direction of rotation will be, opposite. Here it has been here, you can see 1.5 Fm again here for positive case. For negative it will be like this, 1.5, 60 degree ahead. But you will see 1.5 Fm is again there. That means because of this flux, because of this MMF, the reactance gets involved. So 1.5 Fm in this case, 1.5 Fm in the negative sequence voltages. So the positive and negative sequence voltages, sequence impedance will be same. Now the important is that when the zero sequence voltage are applied to this is the axis of the different magnetic fields for phase A, for phase B, for phase C. When the voltages are applied, at that time they will not have any voltage lag or voltage lead. VA will be like this. VB will be same also, because there will be no phase difference, there will be no magnitude difference. VC will also be same. And at point P, VA is equal to Vmax, VB is equal to Vmax, VC is equal to Vmax. They will have a positive value, not negative value. That means at point this is FA, this is FB, this is FC. The total flux, because resultant flux here it was 1.5 mF, resultant flux here it will be equal to 0. So net flux due to zero sequence flux will be equal to 0. That means Z0 or X 0 is proportional to 5. It is proportional to this F will be very close to, because practically it will not be equal to 0. It will be very small. That is why Z0 for the synchronous machine is close to 0, or we have taken this to be 5%. So I hope this is you understood this. For silent pole, since again Z1 is Zd, but Z2 is equal to the average of Zd and Zq, because the Zd is the direct axis impedance, Zq is the quadrature axis impedance, and quadrature axis impedance is smaller as compared to Zd. So this Z2 will be smaller in that respect, and Z0 is again equal to very close to 0. It will be very small. So, but in practice we always take Z1 is equal to Z2, but this Z0 is always taken to be very small. So this was about these values. Silent pole is this, and transmission line, we know that it is equal to Z1 is equal to Z2 is equal to Z0, that is equal to Zn. It is usually close to 12% for practical purposes. And for transmission line, Z1 and Z2 are very small as compared to Z0. We have derived it. Z1 is equal to Zs minus Zm, Z2 is equal to Zs minus Zm, Z0 is equal to Zs plus 2i Zm. There is not a particular value for this case, but This is how you can recall different values and different values relation between the positive sequence and negative sequence impedances. Now, finally, we will discuss some important observations which we have already discussed uh, for balanced system, for unbalanced system, for any system, because we discussed first the symmetrical fault for the balanced system. So we know that for balanced system, IA plus IB plus IC is equal to 0. It is not that balance which we had earlier discussed, that is 18 minus 8 minus 10 will be equal to 0. This is the case when IA magnitude of IA plus magnitude of IA is equal to IB is equal to IC, and angle between IA and IB and IC is 120 degree between each other. So writing deriving the positive, negative and zero sequence currents, we can write it as, we can derive it from this matrix, and I have written as IA is this, IB is this, and IC is this. IB will be equal to A square times IA, because when IA is rotated to 40 degrees, it will be equal to IB because their magnitude is same. Similarly, when IA is rotated this 8 times, it will be IC. So IB will be equal to 8 times IA, and IC will be equal to 8 times IA. So from this, IA will be equal to 1 by 3 IA plus IB plus IC, because this multiplied by this multiplied by this multiplied by this. Since IA plus IB plus IC is equal to 0, this IA1 will be equal to 0. So IA1 will be equal to 1 by 3 IA, that is this multiplied by this IA. A multiplied by IB is AIB. A square multiplied by IC is A square IC. So 1 by 3. Now IB is equal to A square IA. A square into A will be equal to A cube IA. And IC will be equal to, sorry, A square IC, and IC will be equal to A into IA. A into A square will be again equal to A cube. This A cube is equal to 1. This A cube is also equal to 1. That means this will be equal to IA plus IA plus IA. That is 3 times IA. That 3 and that 3 will cancel out. IA1 is equal to IA. Similarly, for IA2, it will be equal to IA1 into IA, A square into IB, and A into IC. A square IB into A into IC. But IB is again equal to A square IC, IA, and this IC is equal to A times IA. Sorry, this is IA. So this A into A square will be equal to A cube into A. A cube is 1. This will be A into IA. This will be A square into IA. Sorry. When I is taken into common, this comes out to be 1 plus A square, and this will be 0. That means IA2 is 0. You can see for balanced system, there is only positive sequence network currents. There is no zero sequence currents. There is no negative sequence currents. So for 3-phase balanced system, only positive sequence components will be present. Zero and negative sequence currents will not be present. For a 3-phase system, if the 3-phase system is unbalanced, all sequence networks will be present if neutral is grounded. If the system is unbalanced and ungrounded, only positive and negative sequence currents will flow. In the neutral wire, only zero sequence current can flow. For the zero sequence current to flow, neutral should be grounded. For a flow of positive and negative sequence current, return path through the ground is not compulsory, or the condition of the neutral has no effect on the flow of the positive and negative sequence current. This is the broad observations from the study we have done so far for balance as well as for unbalanced system. Hope all this is clear to you. Thank you. So